Welcome to Khetz Tutorials, and in this video, so this is basically a continuation of where we left off in the previous video. If you haven't watched that, please watch it. And in this video, we're basically gonna talk about, so the previous video is about ratios and proportion. In this video, we're gonna start talking about triangle theorems or theorems. So let's start with theorem 1. So theorem 1 says a line drawn parallel to one side of a triangle divides the other two sides proportionally. Right? So previously looked at ratios and proportion. Now this first theorem says a line parallel to one side of a triangle divides the other two sides proportionally. So let's contextualize this, or let's view this graphically, right? So I'm gonna attempt to actually draw a triangle which looks good, if that is even possible. Okay, so let's take that. So now let's come back to the theorem. It says a line parallel to one side of a triangle. So let's draw that parallel line which we're talking about. So now we have a line here, and we are saying this line is parallel. Excuse me, let me turn this off and actually, okay. So this line is parallel to one side of a triangle, and we're told that if this is the case, then this red line actually divides the other two sides proportionally. So we have A, B, C, then we have D, E. So we have to actually prove this. We have to write this mathematically or in a way that actually makes sense to us. So this parallel line, the red line, it's in parallel with one side, and it divides the other two sides proportionally, which means the ratio of AD to BD is equals to the ratio of, so before we make any conclusions, we just have to know how to prove this theorem. And after proving this theorem, or after finding out if this theorem is actually true, so that is what a proof is. So we have to have a proof, and what we want to prove is that the ratio of AD and BD is equal to the ratio of AE and EC. So you'll notice that this AD and BD are found on that side, and AE and EC are found on this side. So each of the lines which are taken into a ratio are actually corresponding lines. So you can see that AD corresponds with AE on the other side, and BD corresponds with EC. And by corresponding, I just basically mean they occur at approximately the same position. So if you were to look at the left side, you'd find AD. If you were to look at the right side, you'd find AE. That is what I basically mean. Now the theorem says a line, so we know for sure that we have a line that is parallel to one side. Now we want to prove that it actually divides the other two sides proportionally. That is what we want to prove now. So you're going to start your statement. If you're asked to prove this, you're going to start your statement by saying rule to prove. So rule to prove without the box, of course. So the required to prove, the R is for required actually. So required to prove R to P, required to prove that AD over BD is equals to AE divided by AC. So to prove that, we're going to come back to a diagram over here, and we are going to form some heights, and we're going to add some more lines here. So let's add a few more lines. Then we're going to proceed to prove this. So we're going to add a line from this point D, adding a line from point D to C. Then we're going to add a line from point B to E. Now that we have those two lines, we're also going to add two more lines and these lines are to compute our perpendicular heights. So that is to compute our perpendicular heights. So from D to that point somewhere there, that is going to be a perpendicular height, and we're just going to take a black line because we're running out of colors, and we're going to move and do the same thing to find a perpendicular height somewhere there. So now we have a perpendicular height. So this is, let me turn this off. We have a perpendicular height there, and we have another perpendicular height there. So you can call the yellow one, let's call it K. So the yellow one is K. K. And the black one, we can call the black perpendicular height H. So the H and the K are for the yellow and the black, which occur inside ADE, triangle ADE, right? So we're going to call, let me just write this next to them and clear this up just so it's a bit neater. So let's clear this up here. Have E over there, and we have, so the black one is H, and the yellow one is K. Okay, we can now proceed to prove this. So to prove this, we're going to say the area, using a different color of course, the area of triangle ADE. So just quickly identify ADE in the diagram. So ADE, triangle of ADE divided by the triangle of the area of, so the area of triangle BDE. So ADE and A and BDE. BDE, which is formed by the green line, the red line, and this black line. So BDE. Let's find what that can be. Now we can actually choose which base to use for ADE. As you can see, we can either choose AG as our base, or we can choose AE as our base. But now, for our purposes, to actually prove this, we want BDE and ADE to have the same bases. And so we're going to say a half base, the base which, so we, let me just correct that. We don't want ADE and BDE to have the same base, but the same perpendicular height, right? And to have the same perpendicular height, we look at the vertex which is actually shared, and the vertex shared, which comes back to what we discussed in the previous video, is E, right? So E is common between ADE and BDE. And the base which we're going to choose to find common perpendicular height is AD. So half AD multiplied by that perpendicular height of H, which is the black line, divided by half. And the base which corresponds with that perpendicular height of H is BD. So half multiplied by BD multiplied by H. And there we basically have that. And you can just cancel the H's out and the halves out as well. And you'd have AD divided by BD. So AD divided by BD over there. That is the result after dividing the area of ADE by the area of BDE. We now move on to find what we get when we divide the area of triangle ADE again, but this time we divide it by the area of triangle CED. So ADE with CED, the common vertex is D, and we can choose our base for ADE, in this case to be AE, and we're going to have our area as half AE multiplied by K, which is the yellow line which you have in our diagram. The yellow line, when choosing our base to be AE, remember we said in the previous video that AE, or the base, is the one that actually decides where we have our perpendicular height. So the height is always with respect to the base. Having our base as AE means we actually take our K as our perpendicular height. So now that is the case, we're also going to take K as our perpendicular height for CED, and therefore we're going to have our base as BC. So the base, or the height, is chosen with respect to the base, and the base, which is going to give us a perpendicular height of K when we find the area of CED as EC. And after that, you're just going to cancel those out, and the result of that would be AE divided by AC. But if you look, we have not actually concluded, or we have not actually proved that AD divided by BD is equals to AE divided by AC, because there's nothing that actually connects these two currently. But let's look. There actually is something that connects the two, right? Because if you look at the last point which we discussed in the previous video, we said that the last point said triangles found between parallel lines, and these triangles actually have the same base or equal base. So if you look at BC, it's common among BDE, or it's common between BDE and CED. So CED and BDE have a common base of DE. Actually, it's DE which is common among these two. So they have a common base of DE, which is found in both of these values. So yeah, that's basically it. DE is common. So this one has ED, this one has BD, which is basically the same line. So we can say they have an equal base, check. And they're found between parallel lines. We have these symbols which show that the lines are parallel. So they have parallel lines or occur between parallel lines, check. And the theorem or the rule which we discussed in the previous video says that if two triangles, or if triangles are found with the same base or equal base and are found or situated between parallel lines, then they have equal areas, which gives us this conclusion that the area of BDE is equal to the area of CED. Now that we know these two to be true, you'll notice that this actually means that the area of BDE is equal to the area of CED, and at the top we have ADE, or the area of ADE. So we know that the area of ADE is equal to the area of ADE. We now proved that the area of BDE is equal to the area of CED, and therefore we can finally link these two and say AD divided by BD is therefore equals to AE divided by AC. So the top parts are equal and the bottom parts are equal, which means this is equal to that. And we have ultimately done our proof. So as a recap, you basically compute the areas of ADE and BDE as well as the area of CED. Then you later prove that the area of BDE is equal to the area of CED, and from that you can conclude that AD divided by BD is equal to AE divided by AC, and that is basically the proof of this theorem, this first theorem, that says a line drawn parallel to one side of a triangle divides the other two sides proportionally. So the proportion or the ratio which you have here will be equal to that one, and therefore this line has successfully divided each part or both of the sides proportionally, as the theorem says. Now this has been a long video. I'm just gonna talk about one last thing which is linked to this theorem, and we're going to close this video and continue in the next video. So we have corollaries, and these are basically consequences of our conclusion. So consequences of our conclusion. So now that we concluded that a line parallel to one side divides the other two sides proportionally, we can have consequences from that, or we can conclude that this means that, so let's come up here. So we have our corollaries, if I could just say that right. And these are as follows. I just wanted to scroll up so you can actually view the diagram. So these are the consequences or corollaries, and they say AB divided by AD. So from this relationship, we can conclude that AB divided by AD is equals to AC divided by AE. That is the first conclusion you can make. The second one says AB divided by DB is equals to AC divided by EC. The third one says BD divided by DA is equal to CE divided by EA. And the final one, which we can conclude, or the final one which we can talk about, says BD divided by BA is equals to CE divided by CA. And if you're given a problem and you have to apply this theorem, and you actually apply it quickly, you always, so in math, you always have to provide reasons for the stuff which you did. So if you were to provide the reason, or if this were the reason for you doing something, then you'd actually the notation for that would be, in brackets, line parallel to one side of triangle. So that is basically it in this video. I just wanted to show you how to prove this theorem and make you understand this theorem. And in the next video, I'll be continuing with this theorem, but looking at the converse of the theorem. And as always, I'll do examples just so you know how to apply all of this. And I just want to keep this video short. If you haven't subscribed, please subscribe. And if you like the video, just go ahead and give it a thumbs up. And I'll see you guys in the next video. If anything is unclear, please leave a comment.